This is Dr. Holt. This AP Physics lesson is on collisions in 2 and 3 dimensions. For one-dimensional collisions, the direction of the initial and the final velocity vectors could be specified with just a plus or minus. We were either going to the right and left, or we're going up and down. When you're talking about 2 and 3-dimensional collisions, then they become a little bit more complicated because we have to consider the x, the y, and the z directions of the collisions. As specified earlier, elastic collisions typically are going to be harder than inelastic or perfectly inelastic collisions. When you get into elastic collisions in 2 and 3 dimensions, they're even more complicated than what we've already covered. The figure below shows an off-centered collision between an object of mass m and m2. m1 is moving at a velocity of v1 initial parallel to the x-axis toward the object of mass that is initially at rest. So this object here is at rest. This type of collision is referred to a glancing collision, meaning that they're no longer going along an axis that is parallel to just the x and y axis. The distance b between the centers measured perpendicular to the direction is called the impact parameter. After the collision, object 1 moves off with a velocity of v1 final, making an angle of theta 1 with the direction of the initial velocity, and object 2 moves with a velocity of v2f, making an angle of theta 2. The final velocities depend on the impact parameter on the type of force exerted by one object on the other. When we're talking about inelastic collisions, again, the only thing we need to consider here would be the conservation of momentum in either 2 directions or 3 directions. It could be the conservation momentum in the x, the y, and the z direction. And again, we will fall back on this equation here, which is mass 1 times this velocity plus mass 2 times velocity, which will be equal to the summation of the masses, since they stick together in a perfectly inelastic collision, times the velocity. Okay, let's look at this problem here. This is an inelastic collision. I'll do that one first. In this case, you have a car driving due north at 25 meters a second. It's going to collide with another car driving due west at 20 meters a second. Suppose the two cars stick together after the collision and the second car has a mass of 125% of the first car. Alright, a good way to set these problems up is always to draw a picture of what's happening before and what's happening initial. We'll set this up as the initial condition. We'll set this up as the final condition. Okay, we'll go ahead and draw an object representing the cars. We have one car driving north, so we'll have it like this. We'll have another car driving west. We'll represent it like that. We'll go ahead and draw vectors to represent the velocities. This car is going west. This car is going north. Now go ahead and label the masses and the velocities. We'll let this be m. We'll let this be 1.25 m because it's 125% the mass of the first car. This is going to have a velocity of 20. We'll make that negative since it's going to the left, and we'll make this 25 because it's going positive. Okay, so what you can say with these type of problems, and I'll scroll down just a little bit, give myself a little bit more space, is we go back to the momentum. Again, you have an inelastic collision. In an inelastic collision, we know this. We know that KE initial will not be equal to KE final. Not in an inelastic collision. But we do know that momentum will always be conserved. So PI is going to equal to PF, and that's what we're going to have to work with. So we'll look at the PI in the x direction first. In the x direction, I'm going to get the mass of this car, because this is the only car that's going in the x direction. So it'd be 1.25 times a negative 20. And that's going to give me my momentum of the car in the x direction. And when I run that calculation, I will get negative 25 m. We do the same thing with PI in the y direction. we look at the momentum. And again, as I mentioned, momentum is always a vector quantity. That's why you got to consider x and y. In this case, we would have the mass, and I should have put m, sorry, I should have put m up there too. We'll have m times 25, and that will give me 25m. Okay, we do know this, that the momentum final in the x direction must equal the momentum initial in the x direction. So we know it must equal to negative 25. And the same thing we know with the y, that py final must also be equal to, let me make this m, I don't know why I'm forgetting those, 25m. That must be conserved. Alright, so let's draw a picture of what's taking place up here. We'll let the masses look a little bit larger because they've stuck together. So we kind of know, and it's not really important, but we kind of know that the velocity is going to go off something probably like this. So now our mass becomes 2.25 m because they've stuck together. So all we have to do in this case is we'll look at the x direction first. 2.25 m times the velocity final in the, we'll say at the x direction, must equal to what we had before, and we said that was minus 25. So we know that Vf in the x is just going to equal to minus 25 divided by 2.25. And we'll run that through the calculator real quick. 25 divided by 2.25, and that gets us negative 11.11. meters per second. Alright, we can do the same thing with the y. We come down here, we know the masses are going to stick together. 2.25 m times velocity final in the y direction. We set that equal to 25 m. Again, we divide by 2.25, and we will get that Vf in the y direction will equal to 1.11 meters per second. So then to find, we'll come up here, to find V final, we just fall back to Pythagorean theorem. We're going to take this value squared plus this value squared and take the square root. That'll give us 15.71 meters a second. And now we need to get the direction. I'm going to circle this. To get the direction, then all we really need to do is we're going to look for this angle here. And I'll make this theta. So theta in this case would equal to the inverse tangent of 11.11 divided by 11.11, which obviously is going to give us 45 degrees. So then you know theta is equal to 45 degrees. Or 135 degrees coming off of the positive x direction, or positive x-axis. Again, very straightforward, and this is really the approach you follow when you're doing inelastic collisions. Alright, let's look at elastic. It's a little bit more difficult. Alright, let's look at this problem here. You have a puck of mass 5 kilograms moving at 2 meters a second, approaches an identical puck that is stationary on the frictionless ice. After the collision, the first puck leads with a speed of v1 at 30 degrees to the original line of motion. The second puck leads v2 with a speed of 6 degrees. The figure below, calculate the speeds of v1, v2. Was the collision elastic? Alright, we're going to figure this out. So let's take this problem here. We will set up our initial momentum. We know that the initial momentum in the x direction, again, this is only as taking place in the initial, would equal to 5 times 2, or 10 kilograms times meters per second. Now we look here, we're going two directions, so we need to figure out what the initial momentum was in the y direction. We set that equal to 0 because we have no motion in the y direction. From this, we do know this. We know that P, F in the x direction must equal to 10. We also know the momentum final in the y direction must equal to 0, because momentum is always conserved whether it's an elastic collision or a inelastic collision. And one of the things we're going to prove on this and whether it was an elastic or inelastic. Okay, so what we want to do in this problem here is solve for the two velocities. So we'll go ahead and write the equation for PF in the x. We do that, we will get 5, which is the mass, times V1, which is this, times the cosine of 30 degrees, plus 5 times V2, which is this velocity here, times the cosine of 60. That must equal to 10. We do the same thing with the y momentum. We'll have 5 times V1 times the sine of 30 degrees plus 5 times V2 times the sine, and we want to make that right there to be negative. Let me make this. You got to be careful with, because you got to make the direction of the momentum meet what's taking place here. And we're going to set that equal to 0. Alright, so in this one you have two equations, two unknowns. You can set this up and solve it using substitution, elimination, or matrices. I'm going to go ahead and set it up and solve this with the matrices. I just find it easier. So my matrices would just be 5 cosine 30. That'd be my, to find my V1, this would be 5 cosine 60. I'll set that equal to 10. On this one, that would be 5 sine 30, 5 sine 60, and a 0. I have a 2 by 3 matrices. I'll go ahead and run that, and when I do, I will get V1, and that, again, that's my final. That would be 1.73. I will get V2 is equal to 1.00. Alright, what we want to do on this one now is to prove whether or not this collision was an elastic or a non-elastic collision. So we need to find out the kinetic energy we had initial. The kinetic energy we had initial would equal to 1/2 times the mass of the object, which is 5, times this velocity squared. That will give me what? 10 joules. Alright, let's see how much kinetic energy we have final. Kinetic energy final, and remember, kinetic energy is not a vector quantity. We go back to 1/2 times 5 times 1.73 squared plus 1/2 times 5 times 1 squared. I'll get my calculator, run that very quickly. Gives me 0.5 times 5 times 1.73 squared plus 0.5 times 5. And that gives me a value of about 9.98. So, and just from rounding, we have approximately 10 joules. So this would be an elastic collision. It's an elastic collision because the kinetic energy is conserved. Alright, I hope this video helps you understand how to do elastic and inelastic collisions in more than one dimension.